In the last part, we have seen what are different crystal structures and what are different slip systems in those crystal structures. Now we'll be looking at what are dislocations and other defects in case of FCC, that is face-centered cubic structure. Let's understand what is face-centered cubic structure is. So we have a cubic structure here, and let's say this atom which is at 0, 0, 0 position. Let's mark some other atoms which are at corners and some are at centers, and these atoms are on 1, 1, 1 plane. Let's mark some other atoms, these red atoms, some are at corners and some are at base center, and this comprises of another 1, 1, 1 plane. And let's mark this atom at the corner which also makes or which also sits on some 1, 1, 1 plane. Now, why are we doing this, or why are we marking this 1, 1, 1 plane? Because we know that the slip system in FCC comprises of 1, 1, 1 plane, that is a slip plane, and a slip direction which is a by 2, 1, 1, 0. And where are this 1, 1, 1 plane? So these are 3 1, 1, 1 planes which we have marked with blue atoms, red atoms, and yellow atoms. And this is a Burgess vector, that is a by 2, 1, 1, 0. So this kind of lattice translation gives us a Burgess vector, that is a by 2, 1, 1, 0. Now let's mark these planes which made up of these blue atoms as A plane. Let's designate this as A plane. Let's designate these red atoms as B plane, and let's designate this yellow atom as C plane. Now when we look at these planes from body diagonal, we can see that the stacking of atoms on this A plane will be in this way, where all the atoms are touching each other. That is why these planes are called as closed packed planes. So this is one type of 1, 1, 1 plane, and this is our Burgess vector, that is a by 2, 1, 1, 0. So this Burgess vector can be marked in different way also. Let me do that. So it can be marked from this position to this position. So this is also a Burgess vector. We'll be seeing why I have marked this Burgess vector in this way. Now we are looking at this 3 1, 1, 1 planes from body diagonal. From this point, let me mark that. So this direction is 1, 1, 1 direction. So this 1, 1, 1 direction is perpendicular to the screen, and thus these planes are 1, 1, 1 plane. Now you have B atoms which sits on this position. So next B atom will sit on this 1, 1, 1 plane, will be at this position and at this position. So these are the positions for B atoms. And what is the position for C atom? So the position for C atom is this. So you have A atom stacking over which B atom sit and over which a C atom sit. So you have C atoms sitting, or the C plane is at this position. Let's put atoms over this. So you have B atoms positions which are marked on this plane A, and you have a C atom which is sitting over here. So you have a C atom sitting over here. So let me explain it to you again. So let us mark these positions. So you have atoms, B atoms, which will be on this position. So another B atom will be on this position. Another B atom will be on this position. And C atom will sit here. So C atom will be at this location. So this comprises of this 3 1 1 1 plane. Stacking of this 3 1 1 1 comprises of your FCC structure. So we have a stacking of ABC stacking, and this makes your FCC structure. You have another stacking also, like AB stacking, and this makes the HCP crystal structure. As we are not going in or looking at HCP crystal structure, so we will not see this AB stacking. We will be focusing on ABC stacking, which makes your FCC structure. Now let's look at the dislocations in FCC structure. So you have A atoms which I have marked here and B atoms which are sitting at this position of A atoms. And let's consider a hard sphere model. So when this B atom or B layer slide over an A layer of atoms, they will slide from this position of B to another position. So you have a lattice translation which is occurring from this position to this position, and that is your A by 2 110. So let us mark this direction. So from this position to this position is A by 2 110. But however, when there is a glide occurs, let's say in this direction, so you retain a crystal structure because this shortest lattice translation vector is a Burgess vector. But however, if you consider the hard sphere model, this translation of B atom or gliding of B atom over A atoms will not occur in this fashion, rather it occurs in this fashion. So you can say that these atoms move from this position to this position and this position to this position. Now we have marked these positions in previous slide. You can see that these were B positions and this is C position. Let me mark with another color. So this is your C position. So these B atoms, when it translating from one B position to another B position, they are moving via C position. And you can say that this B to B position is A by 2 110. And we will be looking at what are the splitting of this dislocation in these two, we can say as partial dislocations. Why? Because this B position to this position will retain the crystal structure, while when atoms move from this position, so we can say that when atoms move from B position to B position, it retains the crystal structure, but when atoms move from B position to C position, it creates some kind of a fault. We'll be looking at it. Now let's look at this FCC crystal structure, and I have marked this 111 plane, and let's focus on these points, like these points at corners and these points at these three face centers. And let's make a tetrahedra here. So what we have done, we have joined all these atoms together, and this makes a tetrahedra. So you can see this is a front face and these are all faces, and what will be the edge here? So these edges, let me write it down. So these edges will all have magnitude A by 2 110. So this is called as Thompson's tetrahedron. So edges of this tetrahedra will have magnitude of A by 2 110. Let's mark these 4 points of this tetrahedron. So we have O, which is 0 0 0, then A, B and C. Let's mark the coordinates also. Let's say this is X direction, this is Y direction, and this is Z direction. So let's mark the coordinates of these points. So we have coordinates of these points which I have mentioned over here. And when we say that the B atoms glide over A atom, they move via C position. So let's consider this plane. Let's consider this plane which is OBC, that is O, B and C, and let us mark the Burgess vector here. So we have translation which happens from B to C. Let's mark that. So this is our Burgess vector. So you have this, let me mark it here. So this is also A by 2, 1, 1, 0. So when this atom moves to this position C, it doesn't follow this path, rather it follows a path which goes via C position. And from here you can see that this C position, when I join this, let me draw it. So when I have B, B and B position, let me draw it here. So this C position is centroid of this triangle. So this is an equilateral triangle and this C becomes a centroid of it. So let's mark this position here. So B atom moves to C atom or C position via this splitting of this Burgess vector. So let's mark this position as D. So let us see how is it happening over this tetrahedron. So you have this atom, you have this atom B moving to position C, and it moves from the centroid of this triangle. So let me mark that. So it moves here. Let's consider this as D, and we can find out what are the coordinates of this point D as 1 by 6, 1 by 3 and 1 by 6. Now you can find out what are the Burgess vector. Let's consider this as B1, B2 and B3, and let's mark the vectors along it. So you have B1 as A by 2 bar 1 0 1, and B2 and B3 are A by 6 2 1 1 1 type or 1 1 2 type. So we have seen that this dissociation of Burgess vector B1 into B2 and B3 earlier also. Why it should dissociate? Because the B square, that is B1 square, is greater than B2 square plus B3 square. This we have seen. So this dissociation of B1 is feasible in B2 and B3. So you can say that this Burgess vector can dissociate in B2 and B3, and we'll be seeing its implication very shortly. So now let's consider this atomic arrangement, which we have this A atom, B atoms and C atoms. So this is an ideal positions for forming an FCC structure. So this is the ideal stacking of ABC, ABC in case of FCC structure. Now here I have marked A layer and B layer. So you can see that this is an A layer and these two are B layer. Now if you see these positions or these atoms, you can see that, let me mark here. So you can see that these are B positions, but these are not B positions. So these are not meant for B layers, or these positions are not meant for atoms in B layer. Let me mark that also. So you have B position here and these atoms are shifted to this position. So all atoms from here are shifted to this position, that is from B position they have been shifted in this direction. Now if you look at this region also, so here you have perfect B stacking, that is ideal B stacking over A's atomic layer, but these positions of atoms are shifted with respect to this position of atoms in this way. So let me mark that also. So this position, if it wants to be on ideal B position, so they should move in this way. So these atoms have been moved in this way, and these atoms should move in this way so as to make this layer a B layer. Now what you can see that these B atoms are moved to C positions. So these are all C positions. So all these atoms have moved to C positions. So this is nothing but a C position. Now we have looked at the dissociation of Burgess vector, but now let's mark this layer as a C layer. So this is a C layer. How this has formed? So this has formed by, so if these B atoms would have moved from this position to this position, it wouldn't have created a fault here. What has happened here? These atoms have moved to C position, and thus there is a creation of a fault in this stacking. So you have a B layer atoms here, and in between you have a C layer. Now if I look at this region, I can mark this as a dislocation line, and I can mark this as two partials which are dissociated. So you have a dislocation, and these are two partials, and these partials are called as leading partial, and this is called as a trailing partial. Now what have happened here is that you have A layer over which you have B layer, but in between you have a C layer which has formed. So this is a surface defect. So this is a surface which has been have a fault in this region, and this is a 2D or a surface defect, and this is called as a stacking fault. Why? Because this layer, if it would have been complete B layer, there would not have been any fault, but what has happened in between, there is a C layer which has formed over A layer, and this is not a position of C atoms. So this is a fault which has been created. Why this has been created? Because this dislocation has dissociated into two partials, that is B2 and B3. Here you can see that if I would have had C position here, this would have had stacking ABC, ABC. Similarly, here you have stacking ABC, ABC, which is ideal stacking for FCC. But now what has happened? You have this B layer has changed to C layer, and thus there is a fault which has been created, and this is CA, CA, BC. So this is not an ideal stacking for FCC. So we have a fault which has been created here. And this fault, you can see, is bound by two partials, which is B2 and B3. Now we have seen this dissociation of B1 into B2 and B3, and these partials, this trailing and leading partials, these two partials are called as Shockley partials. So these Shockley partials are of A by 6 112 type. Now why this dissociation happens? Let's consider the energy of a dislocation to be alpha GB square, where B square here is a magnitude of this Burgess vector. And when we find energies of these dislocations, which comes out to be alpha G A square upon 2. And for this two partials, that is Shockley partial, it comes out to be alpha G A square upon 6. And when we consider this, so energy of this dislocation, that is B1, will have alpha G A square upon 2, which is greater than alpha G A square upon 3. And that is why this dislocation, that is B1, dissociates into B2 and B3. Now this dissociation of the dislocation in partials is not straightforward. What do I mean by that? So every dislocation can dissociate into partials, but this is not straightforward. Why? Because these dislocations or this partial dislocation comprises of or creates a stacking fault. When this B1 dissociates into B2 and B3, it creates a stacking fault, and this stacking fault has energy, and that is being designated as gamma SFE, and the units are millijoules per meter square. So these two Shockley partials comprises of stacking fault. Now let's look at this scenario. Let's look at this B1 dissociates into B2 and B3. Let's mark these dislocation lines and let's mark their Burgess vector as B2 and B3. Let's mark the equilibrium distance between this B2, these two partials to be D. And let's mark the length of these dislocations as L. And as I mentioned you, this B2 and B3, that is these two partial, will create a stacking fault in between them. So you have a stacking fault which has been created because of the dissociation of this dislocation into B2 and B3. Now let's find out the components of B2 and B3 along this dislocation line and perpendicular to dislocation line. So this will be a screw component and this will be an edge component. Similarly, you can find out a screw and edge component. So you have a screw component here for B3 and an edge component for B3 here. Now we can find out what is the force between these two dislocations. So this dislocation will exert a force on this dislocation, that is here. So let's consider this dislocation to be stationary, and let's consider that the force exerted on this dislocation, that is a force exerted by B2 and B3, is given by this relation, where that is a force, that is a total force exerted by B2 on B3 will be force between H components and force between the screw components. And we are considering only glide force, we are not considering any climb force here. Now what we can find that the force, let's say F is the force per unit length of this dislocation. So you have length of this dislocation L, so total force exerted will be FL, and this will be balanced because this gamma SFE will create an energy and this force will repel each other. So these H components will repel each other, while this gamma SFE will, because this is a stacking fault energy, so let me mark it here. So we have a stacking fault energy here, and this should be minimized. So material will try to minimize, so there will be an attractive force. So this will be minimized if this area or this region is minimized. So you have a repulsive force between dislocations and you have an attractive force because of the formation of stacking fault, which has energy associated with it. So this force is balanced by a force because of the formation of stacking fault energy. So that can be given as gamma SFE into L, which is L into D, which is area of this region. So this force balanced will give us what is an equilibrium separation between these two partials. So this equilibrium separation between two partials is given as D is equal to F upon gamma SFE. And to quantify this, you can find out this F to be G into B2 dot B3 upon 2 pi. And now what is an implication of this relation is that you can see that when gamma SFE is higher, that means D is smaller. So when material has higher stacking fault energy, the separation between two partials will be smaller. When the gamma SFE is lower, that is, then D will be higher. So when material has lower stacking fault energy, the separation between two partials will be higher. This is very important point. Now let's look at what is an implication of stacking fault energy and cross slip. So we have mentioned cross slip. If you remember, cross slip happens only for screw dislocations. Now let's consider a screw dislocation case here. So we have a screw dislocation. So this is a dislocation line and the Burgess vector is parallel to this dislocation line. So you have this screw dislocation, and this screw dislocation can split into two partials. as 1 by 6 2 1 1 or 1 by 6 1 2 bar 1. Similarly, here also you can see that this dislocation can split into two partials, and the region between these two partials is nothing but a stacking fault. So this stacking fault is being marked here with a shaded region. And mind you, this is on happening everything on 111 plane, because 111 is a slip plane for FCC structure. Now, when this dislocation, that is a screw dislocation, splits into two partials, it doesn't remain a screw because it makes some angle with a dislocation line or a tangent vector, and thus it doesn't remain a screw. So if this kind of a dislocation wants to cross slip, what we need is that these partials should meet each other, and this meeting of this partial again is called as a constriction. So this is a constriction to form a perfect screw dislocation here, and this screw dislocation can dissociate again in these two partials. Now let's look at this scenario, how this cross slip occurs. So you can say that this is the region between these two partials is a stacking fault. Now if these partials will not have a screw nature, thus it cannot cross slip. Only a screw dislocation can cross slip onto another slip plane. So if this dislocation has to cross slip, what it has to do is that these two partials should combine with each other. So let me mark here. So let's say we have partials here. So these two partials should combine something like this, and this is called as a constriction. So these two partials will combine here to form a perfect dislocation. Now this is a screw character, and this screw dislocation can cross slip. So this is a third stage. So now this screw dislocation can cross slip onto another slip plane, and this, when it cross slips, it can again split into two partials on this slip plane, and thus a cross slip can occur. If these two partials has to come close to each other, what is a required condition is that the stacking fault energy should be higher, because what we have seen that, let me write it down, D, the separation between two partials, can be given as F upon gamma SFE. So gamma SFE is higher, this separation between two partials will be smaller and smaller, and thus the constriction can happen here. So there are certain observations, important observations, which can be made using these two relations, that is D is inversely proportional to gamma SFE, and sigma, stress in the plastic region, can be written as K epsilon to the power n, where n is a strain hardening exponent. Now let's consider this effect of gamma SFE on separation of these two partials and its effect on strain hardening. So when this SFE, that is the stacking fault energy of a material, depends on material or a crystal structure or a composition. This stacking fault energy determines the ability of dislocation to cross slip, and in turn strain hardening characteristic. So as we said that the stacking fault energy is, when I say high stacking fault energy, if this stacking fault energy is high, this separation will be smaller and this constriction can happen, and this can make cross slip easy. If the cross slip is easy, there will be lower work hardening. That means I don't have to put too much stress to move the dislocation. So when I say that lower work hardening, that can be quantified using this strain hardening exponent, that is N. So when I have easy cross slip, this N will be lower and material exhibit wavy slip. Why is it exhibiting wavy slip? Because this dislocation can cross slip over here, so you can see that it forms a wavy slip nature. While if gamma SFE is low, the D, that is separation between these two partials, is high, and it is very unlikely that these two partials can combine, and thus cross slip becomes difficult, and thus it leads to higher N, that and material exhibits a planar slip. So that means these two partial can move on only on this plane, it cannot cross slip. So this is an implication of stacking fault energy on a deformation behavior. So you can say that as stacking fault energy is higher, you have lower work hardening or strain hardening is lower, because dislocations can move easily or it can cross slip easily. But when you have low stacking fault energy, you have higher amount of strain hardening, because dislocation cannot cross slip and you need more force to move these dislocations onto this plane. Now when you look at any standard textbooks, see this dislocation or dissociation of this Burgess vector, here I have marked as B1 into B3 and B2, that is two partial, will be denoted by this SFE ribbon. So let me write it here. So this is, you can find it in any textbook as SFE ribbon. And where you have this faulted region, which is nothing but stacking fault, marks SFE. And you can see that when this dislocation moves, it has a slipped region and it has a no slip region. So you can see this kind of representation of stacking fault enclosed by two partials, that is B2 and B3, when B1 dissociates into B2 and B3. So what I mean is that you have this dislocation which dissociates into two partials and in between lies a stacking fault. Now let's look at stacking fault energy for different materials or metals and strain hardening exponent and a slip character. So you can see that the stacking fault energy for stainless steel, copper and aluminium. So you have low stacking fault energy, you have high stacking fault energy and you have medium stacking fault energy. And you can see that the strain hardening exponent, so when stacking fault energy is lower, the strain hardening will be higher and thus the strain hardening exponent will be higher, that is here it is 0.45. Let's say for aluminium, the strain hardening will be lower and it has a strain hardening exponent has to be 0.5. Whereas for medium stacking fault energy, for let's say for copper, the N value is 0.3. And you can see that the slip character, so for stacking fault energy is lower, so dislocations can move only on one slip plane and thus the slip character is planar. While in case of aluminium, these dislocations can cross slip easily and thus it gives a wavy character. In case of medium stacking fault energy, you have both planar and wavy character. Now there are two types of stacking faults which form in case of FCC, and these are, let's say you have ABC stacking for an ideal situation. Let me mark it over here. So you have ABC stacking, and here in this case you can see that you have ABC, AB, AB. So this AB stacking, which we call it as, I mentioned you in previous slide, so this is kind of a HCP stacking. And this kind of HCP stacking in FCC sequence is called as an intrinsic stacking fault. Now here in this case, you have ABC, AB, AC, ABC again. So here you don't have AB or AC stacking, which is comprises of SCP stacking, that is absent over here, and this type of stacking fault is called as an extrinsic stacking fault. So intrinsic stacking fault is what? Where you have AB stacking or AC stacking or BC stacking, which is nothing but a stacking for HCP crystal structure. So if that is present in case of FCC crystal structure here, that is called as an intrinsic stacking fault. While if you have ABAC kind of stacking fault, you call it as an extrinsic stacking fault. Now how to find out this stacking fault energy? So let me briefly tell you how it has been done. So this is called as a gamma plot. Let me write it that also. So this is called as a gamma plot. And how it has been calculated is that what you do, you have, let's say in this case, you have ABC stacking. So what you do is that you move this B layer over A layer by these translations, let's say along 110 direction or 112 directions. So here you can see that this is 112 direction. So if I move this B layer along 112 direction, you can get a minima or maxima because of the positions or these values present on A, and thus you have variation in energies. So here you can see that there are 2 points which have been marked, that is P and F. So P is nothing but a perfect lattice position and F is nothing but a faulted region. So you can say that if I move from this point to this point, I will retain the there will not be any formation of any fault here when I move from P to P, but when I move from P to F, it will create a fault region. So based on this gamma plot, this stacking fault energy will be calculated or evaluated. So with this, I will stop here.